Hello, welcome to another video. We're going to look at general relativity this time, in particular parallel transport. Parallel transport is the motion that needs to be engineered, shall we say, in order for a body moving in a curved space to travel such as its tangential velocity along its curved path always remains parallel to itself. This means that the curved trajectory is made as straight and linear as possible, even though it's travelling throughout curved space. Such paths are called geodesics, but the motion of an object travelling along a geodesic may exhibit seemingly convoluted and odd behaviour to an external observer. Now, I think we ought to make a start and consider the theory along with some examples at the very end of this, what is probably going to turn out to be a series of videos of at least 3, if not 4. So let's make a start and look at what we meant by keeping the velocity of an object tangential to itself as it moves along a curved path. So let's suppose we have a curved path like this going from point A to point B. Now, as the body moves through all these points like this, here, here, and here, and so on, it's got a velocity that is tangential to the point on the curve through which the body is passing. Right? So we've got a velocity vector which is clearly changing as that body moves from A to B along the curved path. Now, left to its own devices, unattended if you like, that velocity will always change and it will always be a curved path, especially as far as the object that is moving is concerned. But the trick here is to engineer a situation, manipulate the mathematics, which we know is general relativity, parallel transport, so that each of these velocities are parallel to the velocity at each of these points. And what we mean by this is, if we have a vector plane like this, with vectors all of equal size and direction in that plane, like that, this is a very simple case of parallel transport. Now, let's just pretend that that is a y-axis and this is the x-axis, and that's V1 and that's V2. Right, now, you might be able to observe that for parallel transport, we might want to, for example, if we're travelling at point A here, we might want to translate that velocity vector to point B there. Now, how do we do that? Well, it's quite simple. You would just, well, take that velocity vector, I mean, kind of say pick it up and kind of place it on that velocity vector. But basically what you would be doing is you would be engineering velocity vector 1 to sit exactly over velocity vector v2. So that if we write down velocity vector v2 there, then we move velocity vector, I'll write velocity vector v1 here again, we move that so that it sits exactly over velocity vector v2. Now that is a very basic example of parallel transport. That is for a linear Euclidean space. So you don't have to do anything like twist these vectors around. It's just a simple case of translating that velocity vector v1 to velocity vector v2. You see that the exact size and the exact direction of both velocity vectors match. Velocity vector v1 fits onto velocity vector v2 exactly. And because velocity vector v1 fits onto velocity vector v2 exactly, there is no angle between either of them. They are directly over each other. So any angle, for example, if the velocity vectors had been configured like this, then you would have had an angle between them. And you would not have been able to map v1 onto v2 with any degree of ease. But this is where, really, parallel transport comes in. Because that's the simplest case. And you don't have to do anything weird and wonderful to really understand what's going on there, or to design mathematics or a coordinate system that helps you to translate velocity vector v1 onto v2. Now, it's a bit of a different matter for a curved space, and I'm going to draw this time this is going to be a curved space. I'll call this y and x as we did before, but this time we have our vector v1, I'll say up there, vector v2 there, might be of a different length as well, and all these other different vectors going in different directions. Now, if we want to translate velocity vector v1 onto velocity vector v2, we can't really do that. As I said, we can't really do that with any degree of ease, because this is not a Euclidean space, and that velocity vector is pointing for a start in a completely different direction to velocity vector v2. It's also of a different size. So what happens when we try to map v1 onto v2? Well, what you actually get is v2 as it is there, and we'll make that a bit shorter because I did make it shorter there. You get v2 there and v1 here. Now, that is quite different from this case of mapping v1 directly onto v2, so that there is no difference between these two vectors in the Euclidean scenario. But here they are separated by, we'll call it for now, an angle theta. It could be an angle phi. There might even be more than one coordinate. So this might be in three-dimensional space like this. with a velocity vector doing something like that, so that it has a coordinate phi along there and a coordinate theta like that. So in that case, you would have two coordinates to consider for that vector. And by symmetry, you can work out what this angle would be there. But ultimately, in this case, you've got two velocity vectors that do not match, either in size or direction. Now, that angle theta is called the covariant derivative. And what the covariant derivative actually means, the actual word that is something that varies according to the variation of something else. So if this vector v1 varies according to the variation of v2, then you have to analyse them together, because they've kind of almost got a dependency on one another. That's basically what covariant vectors means. One vector that varies according or with another vector. Now, there's another word. I think I've actually said it, haven't I? So this is the covariant derivative. And I'll just write that down. So theta is a simple case of a covariant derivative. Did I say covariant derivative before? I should have done. So theta is a simple case of a covariant derivative, and we normally write the covariant derivative as the derivative with respect to our independent coordinates, which we'll call lambda. So we could have actually written theta. So our velocity vector is varying with theta, and so we would write something like that, or dv by d theta. Now, I gave you a hint earlier on that it might not just be one variable that we're considering. There might be a theta and a phi involved, governing the motion of v1 and v2. But you can't, well, you could, I suppose, but what you would want to do would be to kind of lump all these coordinates, like the thetas and phi's, the u1s, the u2s, the x1s, the x2s, the x, whatever you've got, lump them all up into one whole kind of standard form of notation. And so all these thetas, phi's, u1s, u2s, x1s, x2s, we give the name lambda I, lambda superscript I. So in actual fact, we can write the covariant derivative as dv by d lambda superscript I. Now we haven't quite finished, because we'll go back to the pictures that we drew on the board just a few minutes ago. Now, in the first case, the Euclidean space case, if you'll pardon the rhyme there, we've got vectors which are all straight and pointing in the same direction, and they're all of equal length. That's for a Euclidean constant vector space, linear vector space. So if we map this vector v1 onto v2, then it maps exactly like so, such that the covariant derivative theta is 0. So theta is 0. Now that corresponds to this covariant derivative also being 0. So for flat linear Euclidean spaces. I think I'll have to change pen. Right. So this covariant derivative basically describes the extent of the angle between two vectors. And lambda I can be anything within that coordinate system, like a theta, a phi, an xi, a u1 or a u2. They're all individual coordinates or vectors representing something else that affects these two vectors here. But when you see that dv by d lambda I is equal to 0, you know you've got this case. Theta is essentially between the two vectors is 0. Now, in the case of curved space, right, let's just clear this board. Right. In the case of curved space, then we'll just draw our axes again, y and x. Make that black line look a bit blacker. There we are. So we've got vectors all shooting off in different directions, like so. So it's not a very linear space. Now, if we take, again, we'll take for the sake of argument, we'll take this one, v1 and v2. So we've got a configuration like that. We see that the angle theta between these two vectors is not equal to 0. This means that dv by d lambda sub I is similarly not equal to 0. And in general relativity, that's a problem if you want to find the straightest route, the most linear straightest route, which actually we call a geodesic. And the task, and I might as well say this now, the task is to make dv by d lambda I equal to 0 in the equations that we will subsequently get in the next lecture and the lecture after that and so on. The task is to make this 0. Even if you've got a non-linear expression, when you are able to make dv by d lambda I equal to 0, you are effectively linearizing as closely as you can the motion that is taking place. So you might not get absolutely perfectly straight or linear motion, but you're minimizing the curvature as much as you can. And so you're effectively making it linear and as straight as possible. So now, what was I going to? What was the next thing I was going to do? Yes. So basically, what we'll do is just let me get a pen that isn't running out. So if you think about Earth, and that's the equator, and these are the lines of latitude. The equator is the greatest line of latitude, I suppose. So these are lines of latitude, and these would be lines of longitude. I should have really done this in a different colour, but it doesn't matter. Right, let's put another one like that. Okay? Right, so the kind of horizontal circular lines are lines of latitude. These are lines of longitude. There we are. Can't spell longitude, but then I think that should be okay. Longitude. Now, another way of describing the linearization of a variable vector field like this is to describe motion on a sphere, which is a curved space essentially. So let's consider, consider an aeroplane or some kind of other aerial vehicle which wants to travel from A via B to C and back to A again, right? So from A to B to C and back to A again. Now, let's suppose you start out with a vector that's pointing in that direction. So let's suppose that's your velocity vector, or it might be some other vector. Now, as you travel from A to B, your velocity vector is going to change like that. So the velocity vector you started out with up there, whereas that's pointing out, say, horizontally. The configuration of this diagram isn't brilliant, but let's suppose you're pointing out with your arm horizontally. If you just walked around the sphere and you end up at the equator, your arm is effectively pointing south, straight down like that. Now, that's what's happening there. But the trick is to minimise that curvature. And let's suppose we now want to travel from B to C. Then we might travel like this, with our arm pointing due south all the time. I'm sure this would be quite unpleasant if anybody tried it, especially over, say, the continent of Africa. But we're just using it for the purposes of an example. Now, when you get to C, your arm is pointing straight down, and then suppose you want to get back along this line of longitude to A. Then you see your tangential velocity gradually change like that. And lo and behold, what do we have? We have a starting vector that's pointing in that direction and a finishing vector or an end vector that's pointing in that direction. And there's an angle between them, which we'll call theta. I mean, I'm just plucking variables out of thin air here, but basically, that theta, let's call it something else. Let's call it dv by d lambda sub I. It's a covariant derivative. Now, clearly, that is not zero, but we want to make dv by d lambda I equal to 0. Now, again, it's not quite as simple as that, because you're talking about making this angle between the two vectors v1 and v2 disappear. And it's very difficult to do that over a curved surface, because if you make the angle disappear so that that vector is pointing in that direction, then clearly you can't have this sort of motion going right round the lines of longitude, then the latitude along the equator and back along the line of latitude to the beginning A. In that fashion, your vectors will be different. In fact, they'd be twisting around if you wanted to ensure that dv by d lambda I is 0. And this is what we'll get to eventually. You as an external observer, and probably you as the person in situ doing these movements, performing these movements, it will be very odd motion for you. It would certainly be probably quite odd motion to an external observer, because you, as will be shown in some of the examples, in God knows how many videos time, as you go from A to B, and then from B to C, and then from C to A again, you have to do some very kind of odd twisting motions, you know, that ultimately get you back to the point A with the same velocity vector that you started out with. And that's not an easy thing to do, and this is what Einstein worked out. And again, the trajectory along which you move once you've applied all these parameters and conditions and so on, the line that you travel along, it's called geodesic. And geodesics are the straightest lines possible in a curved space, even if they're curved themselves. Light beams, for example, will always travel along geodesics. They will never take a longer route, and there is no shorter route than a geodesic. So a light beam, even if it's being bent by gravitational forces due to a star or another planet, that light beam will always curve and follow the nearest geodesic that it can navigate. So it will always travel along a geodesic, the straightest possible line. So basically, I think we'll leave it there for now, and in the next video, we'll start to apply this knowledge a little bit more to actually arrive at the equation for parallel transport, which is very similar for the geodesic equation. But we're going to concentrate on the equation for parallel transport. So there will be what I hope will be a relatively simple proof of the parallel transport equation. And then we can go from there and apply some more kind of theory and get to a more complex looking solution that we can then apply to practical, if you like, practical real life situations. so where something might be moving through Earth's atmosphere. So I'll bid you farewell for now. Do subscribe, do check out my other videos, and please do come back and seek out updates to this video as well, because I will be putting more up. So thank you very much, and I'll bid you farewell for now. Goodbye.